I remember that we still have something that we left off in the 3D elasticity. But that's about the coding part, and we can come back and wrap it up later. It is not necessary to spend the class time. Well, of course, if I do, I try to complete it. I can record it and go live with you. So we can see how the coding is done, but that is just a detailed thing. So we may not need to spend the class time, which is quite valuable at this point, at this moment, that your examination is gonna start on the 29th of this month, and it starts with the advanced steel structure. I actually trying to figure out what will be the format, the base format for the examination, and it might not need to be the old kind or old-fashioned examination. But we'll see what would it be done, how would it be done. Right. But anyhow, so we will try to wrap up everything within this week. So the both finite elements and advanced steel structures, and I think I deliver more than the promised number of class we have in the syllabus. So we are good right now. Actually, we can practically finish up everything, and what we learn you can compare to other places, that the content that you have learned here is like about roughly 1.2 to 1.5 times of somehow other courses offered elsewhere. Right. So you are in a heavy load. Yeah. I know that. And as I emphasized you quite so many times that well, you have seen that we have everything on the YouTube. You can revisit. When you feel stupid about something, you can revisit and make yourself smarter again when you need. If you don't need, if it is not the condition or situation that you need, you might just keep it there on the YouTube. You can come back later. And if you want to update, well, of course, in the next semester, we're gonna have more things in there. So I will not talk much about the thing I cover already in this semester, actually in this year, from like August semester in 2019 to January semester 2020. So all these things, I don't think I should recover it, or I will just look at to the point where I don't like my teaching, where I don't like the technique of presentation, where I think that it could be done better. I might redo. And what is still like good to know, or still missing, or still like, yeah, basically it's a good thing to know. I'll keep adding it up, so you can check from the date of the video, and you can just revisit all of this and update your sets of knowledge, so it is always up to date, or always like improving, and you will be not how should I say, you'll be learning as much as your junior learns, because as things gets updated, and it is all public, available on the public domain, so there is no reason why you shouldn't update your knowledge, unless you just change yourself to a contractor and get into the other field, the other area. So okay, it might not be useful for you anymore, but it might be useful for the brain, at least, just to make the brain sharp, keep it sharp. Stay away from stupidity. That's the best thing. That's the best policy to live your life in the world. Okay, so we will be talking about structural dynamics. and I'm not going to cover the part that Professor Penning does because he's the best in this area, but I'll be talking with to you about the part that we should know in for the sake of the finite element analysis, or basically we are it can be extended to the knowledge in what the computer method in structural analysis course. So the time integration is actually quite an important thing, and we cannot afford to do all of this in the previous semester when we did the computer method. We code it, but we cannot get to that far, and hopefully in the next semester then I have more time aside from the teaching. I just use the available time to show the coding for the dynamics detailing. So for structural dynamics or time dependent problem, we actually categorize this into two kinds of analysis. So first of all, it is a time domain analysis. The time domain analysis, the name suggests very clearly that we are talking about the time domain. So the solution has to be the solution is function of time. That means you're gonna have the t, right, which stands for the time, in your function. Okay, it's gonna stay there in your function. So that will be the part you get the u, the displacement, as a function of t. It could be the function of space, like the coordinates, x, y, z. Okay, but the t is going to be another part that comes in, and it's gonna play a role in your solution. Okay, so for this, in order to be able to obtain the solution, which is a function of t, let me just change from u to the f. Okay, so f stands for all the solutions you need. It could be stress, it could be displacement, it could be whatever, displacement in x and y and z. But how to solve, how to get this? We have been doing a lot in this finite element course before, when we try so many kinds of problems, start from bar, go to the beam, to an elasticity problem, plate bending, 3D, etc. That's a lot of work done. And now what's being done before is just having the f as a function of space. It is a coordinate x, y, and z. So f, your function, your solution, is varying with the, it is like a field function. It varies in the field of x, y, z in the domain. But now we unlocked the t, because you used to just analyze everything just at one moment only, and that one moment is for a fixed t value. So t is not coming into the picture, but now we unlocked, so the t is coming back in. In reality, the static problem is a subset. It's a subset of dynamic problem. So if you have the facility or infrastructure that handles the dynamics, then for sure it can handle the static problem. But the point I try to make is that we have done a lot, but that is just for the formulation in the space. You have not seen any formulation in time. And in order to solve and get all of these, this is what we want. We want to solve this. We want to solve for this. This is our solution. So to come to here, this point, you have a couple of options. If you do the time domain analysis, you have two major options. First of all, you have the so-called the implicit time integration. And another option is the explicit, again time integration. Both of them are the numerical techniques, which can be you can use both of them for the linear and nonlinear problems. But I will talk about the good things about both of them in the use of linear or nonlinear problems. That will be the factors to consider, and you'll be understanding what to do, because up to this point here, when we talk about nonlinear time history analysis, you can develop the codes, but I think 90+% of you may just go for the commercial software. If you are not the person who make a new sort of finite elements, like I did many years back, I make the different kind of element in 3D analysis of the wave propagation problem of the pi. So there is no commercial platform that accommodates my needs, and that's why I have to develop the code for my own. It is not available. But most of you are going to use the commercial software, and as you are going to go into that direction, yes, seeing the code, understanding the code, understanding the logic behind the code is always good. And that's what we do all the times in this course. I am trying to get you to understand what's the logic behind the code, and you understand the code, the software writer, right? So you can use it correctly. And but into the implicit time, into the nonlinear time history analysis, where we can develop the code, we might not. It might take a couple of classes, maybe slots, class slots, to finish it up. It can be done. It is doable. But the most important part is to make you get the idea, or get how to come up with the appropriate setting for the analysis in order to get everything done correctly. All right, so let's see. All this we call it the time integration. And basically you also talk about the discretization in the time domain. So what we did was just for one step of time, as I mentioned. We just disregard any fact about the time, and we just say that okay, what we want to know is just one step, and we have just one short analysis, and that's it. Okay. But in reality, when you extend, when you come to the problem where you consider the dynamic effect, this is the axis of time, and it is actually continuous. So your problem in reality, it is continuous, and we just do not want to introduce too many things into our equation. That's the goal, because if we have n degree of freedom, right, you're gonna need to cast the equilibrium and the number of equilibrium equations in the system of equation. If you are at this point, you should be able to answer that you're gonna need n equations to solve those n unknowns. This is the linear problem, so you need this many. If it is a non-linear problem, you might need more. And now we are good already, right? We are at the situation that we omit the time, and we live our life happily. We solve so many problems, and at one point I say that, well, you still have the t, and the t is going to come in, and that is going to mess the whole thing up if your u is not just the u one value. It turns out to be the u, which is a function of t. So it is not possible, and not possible to solve using our tools. Using the tools we developed it previously. Okay, so here's the technique. So we use the concept of time integration. Well, basically we chop down the equilibrium equation into like a step. So the problem which is continuous turns out to be the discrete one. And as we chop it down into the discrete steps, right? You have the I minus 1, you have the I step, I plus 1 step, I plus 2 step, I plus 3, whatever. So you're going to have a bunch of steps that you will solve for the equilibrium. So at each step, it represents at a given time, okay? And then we use the equilibriums we had. We use the developed and solve for it. But now we have more than just the resistance from the stiffness of the structure. We are having the mass, which is creating the inertial force. We are having the damping parts that creates a viscous term of force resistance. And we chop everything down like this. We name the step like I plus I minus 1, I plus 1, whatever, but you also have the next thing you have is delta t. The delta t is the time stepping size. We're gonna call it this way. And then I copy. I will put the name. Okay. So the name of delta t is the time stepping size. The time stepping size, when you run analysis, you don't need to keep the time stepping size to be identical. That is not necessary. You can modify the time stepping size. Okay. So you can have delta T1, delta T2, delta T3. Well, for convenience, we just keep it the same. But you have the flexibility, you have the freedom to adjust this number if you want. So for example, if somewhere around here you need a lot more resolutions, you might anticipate the nonlinearity. Wait, it's not the same for all of this. Let me do it this way. Copy and paste. Okay, just that. So this is like the spacious discretization or discretization of your domain. It does not need to be the same, identical size for all. So sometimes when some location when you need the finer discretizations of the domain to handle the nonlinearities, there might be some sort of stress concentration in a given area. Then you discretize the space into your mesh is finer in some particular area. That is just to handle that stress concentration problem. Likewise, for the time integration, you can make it like this. So maybe in the first few steps, you may not expect the nonlinearities. And when you find that it is harder to converge, that means the nonlinearity is coming in. Normally, if you have the linear system, you're gonna need just one step to get the convergence. But when your system is nonlinear, once it is, you might end up with the requirement which is more rigorous in order to get the convergence. And if it is nonlinear, it generally is the best way to keep your solution stable and precise is to discretize your time step into the smaller size. So here we have smaller time stepping size for nonlinearities. So once you encounter the nonlinearities, you will just change your time stepping size into the smaller one. This sort of features is actually available in the commercial software that can handle the dynamics. So something like the reset features, restart, not the reset, restart. It depends on the software, but generally the idea is the ability to restart the analysis. So I call it restarting features, but you might need to read into the manual documentation of the software and see how they identify these features, how they call these features. What is this restarting features? In general, the dynamic analysis is carried out in step by step, and then all the parameters are going to be recorded at every time step. So it's gonna look like this. Analysis in one step is done. Move to the next step, move to the next step, like this. And then you have smaller steps, so it goes like this. So the restarting features is gonna restart the analysis from the latest what would be the latest non-problematic step. Might be difficult to understand, but let's take a look about this. Maybe this step, everything is going alright. Just one iteration in order to achieve the convergence. Everything goes smoothly, and then maybe initially you set the time stepping size to be identical. So delta T1, 2, 3, 4, 5, 6, 7 are in the identical size, alright? And then the delta T7 doesn't look like this. It's not this small. It is actually the same size as delta T6. The point is that when you are entering into the nonlinearities, when it is there, your step size, when it is big, it might not be possible to converge at all. So your code will just report that the convergence is problematic. It takes so many iterations, like 20, 50 iterations, and then and still the convergence is not achieved. It is not in that good condition. So the program might stop automatically due to the inability to converge, to get the converged solution. So it stopped here. Maybe at the end of the right at the step I+5, because it is not possible to get the solution for I+6. So it stops here. Now the point is that you have spent time maybe from here to this point here about 7 hours, which is very short for finite element business. So don't complain if you bump up into the situation that the program just stop you, just terminates, and you waste 7 hours. Generally, we run the analysis for longer than 7 hours. So you expect like a couple of days, or sometimes for the really big problem it could be a week. So this is nothing. But still, for example, if you spend 7 hours to come from step I minus 1 to step I plus 5, and then you find that your program kicks you out and it reports that the analysis is not converging at the step from I plus 5 to I plus 6. So you are not going to waste your 7 hours. That's the point. That's why the features, the restarting features is available in the finite element analysis software, especially for those for the nonlinear problem, because they don't want you to waste your time. So the analysis is actually good up to this point here, and there is no need to trash all of this work that has been done in the last 7 hours because of the inability to converge at this step, right? So the code just said that okay, it's gonna obtain the output file that it made during the analysis done previously, and at the step I plus 5 you will generally have the solution. So that includes the displacement at the nodal points, that includes the velocity at the nodal points, and that also includes the accelerations at the nodal points. So all of these are going to constitute the analysis that at the step I plus 5, and then you redefine the time stepping size like delta t 7 to be smaller like this. So it is possible to get the nice convergence. You might need a few iterations in order to get the convergence, and you'll be happy with that, and you don't waste the past analysis. So you can run with the different time stepping size. Okay, so small time stepping size is gonna run from this point on. And once you see that, well, maybe time stepping size you are doing here is like very small, it is too small, you don't want to waste too much time, because small time stepping size, that means more equations to solve, more times to spend. So if you used to have like 5 millisecond time stepping size, and you chop it down into 1 millisecond time stepping size, that means you are investing 5 times more than before in order to achieve the solution over a given the same period of time, right? So when it takes you for long, maybe you go along this smaller delta t, smaller time stepping size, and you find that, hey, wait a minute, I don't see anymore. I don't see the non-linearities anymore. I don't see the iterative solution anymore. It takes just one step and it converge. Take one step and converge. The error is 10 to the minus 100 or something like that, which is so small. And that means just the numerical roundings going on in the software, in the computer, but it is nothing wrong with the scheme, the finite element. So you might figure out that maybe it is not necessary to continue like this anymore, and then you make the time stepping size after this point where you think you do not have the sensitive nonlinear problem. You extend the time stepping size, and then your analysis is gonna run faster. You take less time. Okay, less time is important. Many times it just determines your graduation time. So you might be a little picky with this, and you can say, okay, stop here, enough. I think I covered the nonlinearities already, enough. I don't need this anymore. I need the stepping size to be a little bigger. Yeah. And then you have that features. So it is the features that does the restarting. So whenever you stop, maybe analysis crash. Okay, the scheme just crash. It's okay, fine. You can restart your code. All right. So now the time discretization is going on like this, and at each step you solve, you finish that step, you come to the next step I, you solve the system of equation. You're done. You get the parameters of the step I. You are going to evaluate step I plus 1, and then you solve. So that means a bunch of a big system of equation solving. If you are dealing with elastic, not just a linear elastic problem, your stiffness metric is not going to change. But there will be some other thing that is going to change, but you still can keep using the same K, yeah, for all stepping size. The thing is that if it is possible to reuse the K, that means you save a bunch of time evaluating the stiffness matrix, because we have seen that the procedure is quite rigorous in order to come up with the stiffness matrix. You go from 1 to NELE, and then in each element you have the numerical integration going on. You evaluate the B matrix and B transpose DB at every integration point. You conduct the summation for all integration points, and once you're done with that, you plug in all the entries into the system stiffness matrix, and you plug in a bunch of things. So if you can keep using the K, that is your luck. If you cannot, if the nonlinearity is there, then you need to update your K, your stiffness matrix, and that is going to take you time. The thing is that the features like this is the generally the software might offer to you. So the software might try to streamline and make sure that the analysis will be the fastest as much as possible. Okay. We are having I would like you to look from the overview first. Okay, at least now you know that the equation solving is going on at the discrete points that we chop down into the steps. So over at one point, now let us see, at one point at a given step, at a given time step, we have U, which is the vector. What is the size of this vector? It is n by 1, where the n is a number of the degree of freedom. Total number of DOF. And not only U, right? You're gonna have the U dot, of which the dimension is identical, n by 1. And you have U double dot, of which the size is also n by 1. So what happened now? You used to solve in a static problem. you used to solve for n unknowns. Now you're going to need 3n, 3 times n. If we want to solve the 3 times n unknowns, how many equations do we need? This is a linear problem. The number of equations is going to be as many as 3 times n equations. How do you afford that 3 times n equation? It's not possible, right? You are going to solve differential equation in the way that you used to do in the dynamic class, where we are going to make all of these to be coming from the same thing. Okay, so the u dot and u double dot will be represented by the function of the same variable. These have to be expressed by one variable, and that is going to be the delta u. In order to achieve that, we need a little assumption. If we just follow the straight dynamics problem, we have the equation of motion u double dot m u double dot plus c u dot plus k u equals to force, and we want to solve and you want to get the u, you got to solve the differential equation. But for here, if we just say that if we want to make it possible to present all the variables as functions which is made of one thing, so that one thing turns out to be the delta u. So it is a change of u over that one given step, and that will be possible if you are going to express by using just delta u. You need to have one assumption, and that assumption is acceleration within the step. It is not acceleration at the beginning, it is not acceleration at the end. So if this acceleration is maintained constant over a given step, you can bring yourself back into the physics course. It is a high school physics course when you learn about the equations of motions of the particles, right? So you bring yourself back to that time. But before you go there, let's talk about the A a little bit. The A come from some technique of averaging or weighting of the acceleration from the step I put I here, and the step I plus 1. This step I is the current, we call it current step, and we associate the current step with the sense of having everything being known. Everything was solved already. U dot I and u double dot I are all known, and the step I plus 1 is the step of our interest. In other words, I'm going to say that u I plus 1 are all unknown, and the meaning is it is to be solved. We will solve all of this, but the point is that all of them are not going to be independent parameters. They are all tied up with delta u. So in other words, they are all the function of delta u. So practically, we are going to solve for just one thing, and then from delta u, you can go back and get u I plus 1, u dot I plus 1, u double dot I plus 1. And in order to achieve that, I just mentioned that the acceleration throughout a step is assumed to be a constant value which is equals to a, and a which is weight from step I information double dot and step I plus 1 information u double dot. Okay, right. So yeah, here it is. A is given in terms of the part here times the step I and part here times step I plus 1. If you look at these parameters, whatever the b is, well, b is going to be in between 0 to 0.5. So if the b is 0.5, then the whole thing is 1. Then you do not have any influence from the step I, and you're gonna have the pure influence from the step I plus 1. Okay, so the b is just the factor that gives you the sense of from 0 to 0.5 possible range of the beta. So it gives you the sense of how the averaging is done. If it is the constant average acceleration, the beta has to be constant and average. The sense of average means it is half and half influence from the step I and step I plus 1. So beta is 0.25. 0.25, then you get 0.5 here, and 0.255 here. Turns out that the whole thing is 0.5. So you have half and half of the step before and the step after, right? And now, if you have this average acceleration like this, I think you remember something like the s equals to ut plus a half of at square, right? I think you remember this in your high school physics, where the s is the displacement, and u is the initial velocity, t means the time duration, a half of a is the acceleration, and that is the constant acceleration. What you learned from high school physics, you only have one constant acceleration. You do not apply all the formulas you learn into the cases where the acceleration is not constant. You need to do the time integration properly. But here it is what you learn there assume that the acceleration over a given period of time is constant. Okay, so this is going to be used. But let me ask you, if this is going to be used, what will be the consequence of using the concept or the assumption that the acceleration is constant? In reality, acceleration here and acceleration there are actually different, right? It is different. So constant acceleration scheme is like treating the acceleration to be just one value, whereas the reality, you could have the acceleration like this, you could have acceleration like this, or you can even have acceleration distribution, like whatever profile you can imagine. But to use just the constant acceleration, that means these 2 points, you shouldn't have like a big difference in the accelerations. If it is too big, well, no matter what kind of distribution, linear, quadratic, or whatever, but if it is small enough, the delta t is small enough, then it can be averaged by the constant acceleration. That's my whole point. So you shall not have too big delta t. That's the whole thing. If your delta t is large, the discrepancy is gonna be there. You will not like it, because this scheme simplify your life, and it just needs your cooperations a little bit, and that cooperation is about the time discretization. You shall not have too big time stepping size in order to get the correct solution. Okay, so this is going to be used the s equals to ut plus a half at squared, but let's put the variables in the format that we set up in this class. So s is what? Over one given time step. Okay, over one given time step, your s is the delta u, right? S is the total displacement, which is equals to delta u. You have u at step I, and you have u at step I plus 1, or the next step, let's say the next step. So you have 2u, and if you take the u from the step I minus the u from step I minus 1, you're gonna get the delta u. That's the thing. So delta u reflects the s. It's the meaning of the s. So I put the delta u. What? You used to have just the s, which is just one number. Now just a scalar. Now we have the delta u, which is the vector. So it contains the delta u of every single degree of freedom in the problem. And then s equals to ut. What is u? U in that physics course, it is the initial velocity. So initial velocity of this step is from the I minus 1, right? Okay, we better talk about the I and I plus 1 step to make our life a little easier. So the setup is gonna be like this, and we're gonna make this current step. Okay, so I will be, this is the target. So I'll be consistent with this, right? The step I is the current step. So okay, no more talking about the I minus 1 there. Let's say the I minus 1 has to be known already, right? This is solved already. Okay, so I say explicitly solved it. This is to be solved. Okay, it is the target. Now it is clear, and delta u is going on within just that step. Okay, and it is equals to u of u is the initial velocity, so it is the u dot. Of course, one dot has to be there. For I or I plus 1, it's going to be for I, because we know information at the I step. So the I step is the initial condition. It is the vector u dot I. How about the t? T has to be the delta t, because the time stepping size is equals to delta t. For this case, it is delta t subscript 2, but I will just omit the subscript 2. I will call it just delta t, and we know that it is associated with the step here that we are solving. So delta t is put in there. S equals to ut plus a half of a. A is the thing over here, so I copy this stuff, copy and paste it. There it is, and draw it this way. A half of A and delta T square. Okay, that's it. S equals to U T a half A T square. Right. Now, let's take a look at this together. Delta T is the scalar, right? So you don't see any wiggle like that, which represents the vector quantity. Delta U is to be solved. U dot I is known. Yeah? U double dot I is also known. This is unknown. Okay? Delta U is to be solved. That means it is unknown as well. So what we are trying to do here, from this equation, we are capable of expressing the U double dot I plus 1 in terms of other known parameters and one unknown that we love. Okay, we want to formulate everything in terms of delta U, so we love to express it this way. So this is going to be on one side, and then it will be given by delta U and other parameters which are also known, which are all known. Okay, so let's do that. So first of all, I think I'm gonna have the 2 delta U is equals to 2U dot I delta T plus 1 minus 2 beta U double dot I plus 2 beta U double dot I plus 1. You have the delta T square, right? So we need to take everything to the other side of the equation. And I think I may just, first of all, two delta 2 delta U should be divided by 2 beta over and then delta T square. I take the U double dot I plus 1 on the left hand side. So I take all of this to this side, and then let's say I keep it on this side, but I just switch the view so you can see the U double dot on the left hand side, and I try to get rid of all these parameters, coefficients. Okay, now you get the first part, and then the remaining will be go back to that side, and then that's gonna be the minus sign. So we have next 2 U dot T delta T, and that is divided by 2 beta delta T square. And then what else? The last one, plus 1 minus 2 beta u double dot I delta t square divided by 2 beta delta t square. So we're gonna fix all of this to cancel out. You have just beta to cancel out, delta t cancel out, you have just one left, delta t square is cancelling out, and then you have just that remaining. So that is equal to delta u divided by beta delta t square. That's the first term minus the u dot at the step t divided by beta delta t, and then plus 1 minus 2 beta divided by 2 beta, which is just the coefficient u double dot I. That's it. That's it. And move it up. Okay, that's it. Perfect. Right. So right now the u double dot at I plus 1 is expressed in terms of the one unknown delta u, and the remaining are all known. So I shall just do it this way. I change the color into the maybe this one. Yeah, okay, looks good. So I put the red delta u such that you this is not t, sorry, this is I. So the u double dot I plus 1 is fixed. Now you have another thing that the issue is not yet resolved, which is the u dot I plus 1, this thing. The u dot, just the u, for the u I plus 1, it is very easy. ui plus 1 is equals to ui plus delta u. That's it. This is the easiest one. Okay, this is the second one. Then the last one, the velocity u I plus 1 is not determined yet, and we are going to express the velocity in terms of delta u as well. So we'll see how is it done. Okay. Right now the velocity at the step I plus 1 should be given by the velocity at the step I and plus the acceleration. It is the acceleration times the delta t. The point is that the point is that the acceleration we are talking about right now, it is coming from the different idea of the averaging, or the idea of taking the contribution from the two acceleration points, from 2 points. So the A was actually coming from the 1 minus 2 beta and 2 beta u double dot I plus 1. But for this one here, you have final velocity as the initial velocity plus the acceleration. So this acceleration here is not equal to A. It is just the features of the calculation of displacement. Should it be minus sign for the last term? Oh yes, thank you. Yeah, I should see this. Thank you. Okay. So this one here is going to use the different weight for the averaging. Gamma. And we have the u double dot I plus 1 from above already. You can see there. So u dot I plus 1 will be given in terms of this, which is known because it is the step I. This is also known because it is the step I. This thing is step I plus 1. We're gonna substitute the values we obtained before, which is from the I, and the delta U. So let's do that. And it is equal to u dot I plus this means the 1 minus gamma u double dot I times the delta t, okay, plus gamma times the whole thing. So I have to copy this whole thing and I'm gonna paste it into there like this. Well, the delta t has to be taken, paste, and that's it. 1 and paste, and the delta t. Alright. That's good. And we just need to rearrange terms. So start with the u dot I the video was interrupted for too many times. Good that we are pretty much at the end of this course, and this frustrates me, and when, well, you have no idea if you are teaching and something is not going on correctly about the internet, and I have to worry about the internet, and then I have to worry about what's going on in the course as well. It takes too much of my RAMs, and my teaching efficiency drops quite clearly. Later, I think I should take the video without live, but that's not going to be later because this is pretty much at the end. But yeah, if I want to take a very serious one, I shouldn't hook up to the internet, because internet could be interrupted. Maybe someone in my house just turn on some sort of equipment, iPad, TV, laptop, and that equipment just disturbs the internet, and it is, well, I was kicked off and in so many times. Well, complain too much. U dot I 1 minus this term, so this has to be, I got to cancel the delta t out. Okay, so gamma over beta and delta t is cancel out, so it's gonna look like this. Okay, here we go. Right, now one done. Next it's gotta be the delta U can be taken out, so the delta U will be taken out just right away. It has to be in a minus 1. Delta U is plus, and delta T squared turns out to be just the delta T, and gamma has to be scaling there. So I put this out here, and then okay, the gamma over beta delta T delta U U dot at step I. Okay, so I think everything looks alright. Then we move over to the U double dot. For the U double dot, we're gonna have the we're gonna have this, and that makes it the 1 minus gamma, and then minus 1 over 2 beta plus 1. Okay, plus 1. 1 minus gamma from here, and then you have minus 1 over 2 beta, and minus 2 minus turns out to be plus 2 beta over 2 beta, which is 1. And what? And it is the U double dot I delta T. Wait a second, there must be the gamma there. Okay, and another, which is a gamma there. So gamma cancel out. So what will be left of? Okay, just like this. And this is your U dot I plus 1. There's going to be so much fun doing all this, making the algorithm for all of this, but you will love it when you can see your problem works in the time domain. So these 3 things will be used to constitute the equation of motion. So equation of motion is going to be in the next page. Okay, alright, we have that page. We're gonna put the equation of motion. Equation of motion. The equation of motion will be to be cast at well, let's say to be cast, yes, at this step I plus 1, because we want to solve for the information at the I plus 1 step. So that looks pretty much like this. M, which is the what I did there, okay, correct, mass matrix, multiplied by U double dot I plus 1 plus the C, which stands for the damping, I plus 1 steps again, and the K times the U at I plus 1 equals to external force, which is in the I plus 1 step, and that's it. So we are going to solve this equation. Previously, we used to solve the equation in the red circle. So you used to have only just the K term, stiffness times the U, and that produced the restoring force equals to the applied force from the external. But right now, your inertia force and viscous term are going to come involved in your equation. But you are not scared of that, because this is not going to introduce you more unknowns. You still have just n unknowns aside from 3n unknowns, because acceleration can be expressed in terms of delta U. Velocity can also be expressed in terms of delta U. And the next step, displacement, is going to be expressed by delta U. And that's the beauty of this time integration. So let's plug in one at a time. So we first start with the M mass matrix, multiply with the acceleration terms, right? So I take this, copy, I come to this page, I paste, oh, I don't need that, you double dot, so oops, yeah, this is taken to here just right away, and that's it. You get the M, and then you get the C, and will be taken from the derivation we made again. I keep bringing this in here. Not okay. There it is. Okay. C times the U I plus 1 plus K times U I plus delta U. This is going to be equals to the external force, and this has to be known. You have to know the forcing function. If you do not, this is not possible to solve. So the forcing function has to be always known. You might ask something like, if we are encountering the case where we have the earthquake hitting a building, and this is given by just the ground motion records from the accelerometers. We call it the broadband accelerometer or seismometer. Broadband seismograph. So you have this record of the ground motion during the earthquake, and then you want to analyze this building under that given ground motion. It is not the forcing function, but you apply the acceleration or the displacement time history at the base. So this does not involve with the forcing function like this. This is the applied force. If you have the building, you have the wind, and you can find the force at many locations, and this is given as a function of time. So it comes into this term. But if you have the prescribed displacement like this is going into here. Okay. So at the nodes that you know the displacement, you can just input that displacement information, and you can excite the building or some structure under the ground motion by that technique. Actually, in computer method course, I used to show you how to induce the settlement, right, to the base, to the foundation of the building. So it is the same thing. It is possible to do, but it is just to be carried out in the time equation of motion, which is the extension from the form we used to do before, and that is it. So now let's take a look. This is the set of equation, the system of equation we are going to solve. The part that is known, let me just make it clear. So the I-step information is known. This U dot, U double dot informations are going to be made in green, such that it is easy for us to differentiate. And this is also known, the acceleration, and this forcing function is supposed to be known. Okay, all knowns pretty much. So if you want to solve, then our job right now is to rearrange this equation such that the red are staying with the red and the green are staying with the green. Alright, so finally we're gonna solve for the delta U, the red. So let's bring all of the known together, unknown together. Start from M. M over beta delta T square. Okay. M over beta delta T square. Yeah, that is multiplying to the delta U. What else is multiplying to the delta U? We have the beta. Oops. We have the beta. Gamma. Okay, sorry. Gamma over beta delta T C matrix. Let me just separate the coefficient terms and the matrix terms out. Okay. Plus matrix terms out there, coefficient terms and matrix, and what else? And then plus plus the k times the it's just delta u. Okay, so the k times 1. And then if you notice, you find that the coefficient in front of the m, in front of a mass matrix, it has the 1 over delta t square. 1 over delta t square, if you think of delta u is the change of the displacement, and the change of the location. Okay, let's call it that way. So change of the coordinates or location, and if you divide by delta t, you get the rate of change, which is something like the velocity. So for the damping term, it is scaled by 1 over delta t. Of course, it's going to be scaled by the gamma and beta in order to adjust it to match with the velocity precisely. And also here, change with respect to delta t squared. So now you have the velocity and then the change of velocity that represent the acceleration. So the acceleration term is going to multiply with the mass, which stands for the inertial force. This turns out to be the viscous force, and this is just the static restoring force, which is coming from the structural element resistance. Move this down to here, and then this all scaled by the delta u, right? And delta u is to be solved, which is equal to the following. I'll be doing it this way just to make it short. At the end, ultimately here I want to make sure that you can imagine what is going on and what will be the shape of the matrix that you will see. So 1 second. Right now we group up everything on this side. We took out the red, the part which is associated with the red unknown u vector, right? We put all of them together on the left hand side like before. But now we're gonna move the part that is known back to the right hand side. Okay, so left hand side is finished. Then the green will be going to the right hand side. As it goes to the right hand side, then I need to change the sign just a little bit. And there it is. M is done already. Now next is about the damping term. So I'm gonna move this to the right hand side, but I'm gonna erase out the red terms. I'm gonna just move this in. Okay. What else? It should be just the minus sign, right? Minus sign of this. Okay. We ran out of space. Then gonna put the minus sign down here to make sure that we're not going to miss it. And the last term is going to be the k. So that is equal to minus k times u I plus f I plus 1.
And we have a name for this, right? Effective stiffness matrix. We call it this way. Okay. Effect. Let's look at this. If the K is elastic, if we run the elastic problem, okay. If the C, why do I have that thing in the C? Okay, if K is elastic, it's always elastic. We are working on linear problem. C is not changing. If it is like that, okay, mass matrix is not going to change anyway. So we can repeat. We can repeat the use of effective stiffness matrix. So you don't need to go through like every time. You just cast and you get K effective. And once you get K effective, and if you inverse the matrix, okay, you just keep that inversion and then you just keep multiplying it with the, just keep using this to solve for the delta U in the next step. So let's look at the right hand side. Right hand side will always change, of course. First of all, you have the force vector, the applied force vector, and this applied force vector has to change, right? Because it is a time history, so it's never stationary. It's got to change. What else change? Well, the coefficient like mass matrix, the C matrix or the K may not change. They will not, but the green thing will always change. So this is coming from the previous step. So they ought to change. I need to, okay. That means, okay, right. Looks good. And all of these right hand side here are going to be just the vector. Okay. Right hand side. Vector. You have the matrix and then you multiply by this vector of which the same number of row dimensions. So these two multiplies and then you get the vector. Likewise for this one. Okay. So here actually the meaning, the physical meaning is like the resistance which is caused by the inertia part, and this is a contribution that you had from the previous step. Likewise for this term, it is also the resistance which is caused by the viscous terms. Last one is easiest to see. It is the resistance, it is the restoring force you had from the previous step. So all of these are going to compensate with the applied force. So if the applied force is not changing from the previous step, maybe you don't need the delta U, right, to equilibrate this equation. But there will always be some change. So this is a part that is unbalanced with the applied force F, and then we find the delta U such that we get all equations equilibrated. Okay. point is that if you use the constant average acceleration scheme, the constant average acceleration scheme is actually very robust, so it is always stable, very stable. So you plug in the beta equals to 0.25 and gamma equals to 0.5, so you get the same contribution in order to compute the displacement and to compute the velocity, and they are consistent, right? So displacement computes from the A, and the A average the U double dot from equally from two steps before and after, and also the V is coming from the average, okay, like 50% of this and 50% of this, so they took the equal influence from before and after, and that turns out to make that CAA seems to be a very favorable one. You can go for the beta, which is not 0.25, gamma is not 0.5. That's possible. You can look up, but you might have to well, sometimes you arbitrarily introduce the so-called numerical or algorithmic damping. So you have some damping, okay, which is not real. It is the algorithm caused by algorithm. So that's called the algorithmic damping. You introduce it to your calculation, and that's gonna suppress the response. That means in reality, your structure, your system may not be under this condition. It may not have this damping, but you just arbitrarily introduce it in. Many people introduce this algorithmic damping because of the scheme that they use might not be so stable. Sometimes the formulation that is caused by the formulation of the FEM that might be unstable. So the damping terms that is introduced by the use of the beta, the setup of beta and gamma, which is not like the 0.25 and 0.5 will give the damping that helps stabilize the system. But the difficult thing is that what is the right amount of damping such that you end up with the accurate solution? That is always questionable. So the best way is to stick with the constant average acceleration to avoid those issues. Sometimes you get the unstable solution. For example, if it goes like this, generally your signal should go like this. But when your system is not stable, you're gonna have like something like this, keep going, and keep growing up and bursting out. This is the unstable condition, and I have seen many of these in my code, and generally it is because of the code contains some sort of error. Sometimes the left hand side and right hand side are not consistent, so you can end up with the you end up with the unstable condition, right? Now, this system of equations here, if you want to extend this for the nonlinear problem, it is perfectly possible. Right now, we come to this point, we handle the dynamic of the problem already, right? We can handle the nonlinearities of the problem. So, how to handle the nonlinearity? that's gonna bring you back the old memory in computer method in structural analysis. So the equations we have here, we are going to put everything onto the same side. Okay, and practically you should end up with the zero residual when you get the convergence, or residual should be really close to zero. That's the whole thing. So this term here is going to be placed onto the other side, okay, and the whole thing is going to be set to zero. And once we do that, we are going to express using Taylor's expansion. So we're gonna express the system of the residual equation should it be done today? We have just 5 minutes, right? Okay, just give you the test of what is gonna happen. So yeah, everything will be given in terms of the residual. We're gonna write the equation of the R as a residual as a function of delta U. Residual would supposed to be zero if it converge, and it's gonna be given by the equation we have above. So we're gonna find the tangent stiffness of the residual, and it is going to be the same as computer method course we have seen so far. So we're gonna use the Newton-Raphson for the iterative solution. It can be done in identical way as before. So we'll see. Okay, we have just 3 minutes. We cannot wrap this up in just this class. So next class we come back to this point here where we try to handle nonlinearities, and also we are going to move into the explicit time integration, which is very useful in some sense. I'll be talking about the use of these two things, the implicit and explicit time integration, in the next class. But it is like you are going to deal with some sort of cheap element like triangular element. I used to talk. I told you that it is a cheap one, but since it is very cheap, it makes it possible for us to make a very fine discretization in space for triangular element. So as the discretization is smaller and smaller and smaller, then it is very friendly for the nonlinear problem. Nonlinear problem, if you need the accurate solution, you cannot avoid the discretization, the very small mesh around the stress concentration area. So if you cannot avoid that situation, you just use the cheap element, and that is not going to make difference between the cheap element and the bigger element. Likewise, for the time integration point of view, the use of explicit time integration will enable you to chop down, to discretize down the time domain into the very, very small delta t. And it's going to require a very small delta t. Otherwise, the stability is going to be the issue for the explicit time integration. So it is notorious about the stability issue. But as the time stepping size is so small, then you resolve the stability issue, and the calculation cost is very expensive because the way the system is solved, it is different from the implicit time integration. Okay, for implicit time integration, you can use maybe the bigger time stepping size. Still, the computation is robust. not going to suffer from the instability issue like the explicit time integration. But when you deal with nonlinearities, you still need to discretize down the time stepping size such that the size is small enough in order to make the solution converge easily within a time step. So that brings you to the explicit time integration. Maybe the implicit might be more friendly to you for the elastic analysis, that you might not need to chop down the time stepping size into the very, very small one. So okay, elastic analysis might work well, but once the size is very small, implicit time integration is going to take you so much time in comparison with the explicit one that could be a lot faster. Okay, so the use of the scheme is also important. You've got to understand the nature of the FEM, and then you'll be able to select the right one for the right job. Okay, for today's class, I think it is enough, and we'll be seeing each other again on Thursday. Now I'm trying to figure out how to end the live streaming because I am out of the screen that I had originally. I cannot find the way to finish up to close this down. So okay, I'll see you again on Thursday. All right, bye bye.